Okay, hi everybody. So as promised, here's my cartoon comic book version of why special relativity and quantum mechanics contradict each other. So this is the first panel of my comic book. This might be the worst comic book you've ever seen, so try not to pay any attention to the art. Just listen to the idea. So Einstein, when he developed special relativity, he said that it's not possible for a signal to go from A to B faster than the speed of light. So here, there's A, there's B. A says to B, "Hi, B." And then 1 second later, B gets the message and says, "Oh, hi, A." And I've decided to make them a light second apart. So they're a light second, so light takes 1 second to travel from A to B. That's me right there. Light travels really far in 1 second. It actually travels, that's 300 million meters in 1 second. So if you're 300 million meters away from another object, then it takes 1 second for you to trigger something else at that distant position. Now, quantum physics and Werner Heisenberg said that we don't really know where A and B are. There's some uncertainty in the location of A and B. The thing is, if A and B are 300 million meters apart, that uncertainty doesn't matter. I've drawn in some error bars. It makes it look a little bit like TIE fighters in Star Wars, but they're not TIE fighters in Star Wars. It just indicates the uncertainty. Those error bars would be really, really small if you're talking about a whole light second. Remember, a light second is 300 million meters. That's me again. So the uncertainty is really small compared to 300 million meters. The problem comes when you move A and B really, really close together. When A and B are really, really close together, you can get their uncertainties to be so close that compared to the distance that A and B are from each other, the uncertainty can actually be quite big. So this is me saying, what if A and B are actually really close? Now we got to go over to the other side. Sorry, I could pause this, but I assume you're enjoying the experiment. So relativity, special relativity, doesn't have uncertainty built into it. It says, special relativity says that there's only one position for an object. So light needs to travel that discrete distance from the one dot to the other dot before something can be triggered by the other dot from A to B. So light needs to travel that far, as indicated by the arrow, to go from A to B, and I've called that time a click. So relativity says, and that's a really small time, relativity says there must be at least one click in order for A to cause B. However, the problem is, when you consider special relativity, when you consider quantum physics, first of all, if the particles are on the edge of the uncertainty where they're far away from each other, that's no problem, because it takes more than one click for light to travel from A to B if they're on the ends. The problem is when they're really, really close to each other like this. When they're really, really close to each other, if in fact they are, quantum mechanics, remember, says we don't know where things are. So if they're close together already and we don't know where they are, then they might be so close that it takes considerably less than one click for something at A to cause an event at B. Now, to special relativity, that looks like something traveled faster than the speed of light. And that means that according to special relativity, then cause actually happened before effect. Oops, here, going down here. And that's the problem that the standard model solves, because you have a signal traveling faster than the speed of light, and the only, according to relativity, and relativity can't explain that any other way other than saying that cause happened before effect. That effect happened before cause, which should be impossible, and that's why we need the standard model. Hope that helps.